For this video, I'd like to talk about the unit circle in reference to radians. So you might recall from a previous video that if we have the unit circle, we can essentially draw a triangle where I draw in the hypotenuse and then just drop down a vertical line so that this essentially makes a right triangle here, and we have this angle theta, and this hypotenuse is 1, which is why we call this the unit circle. It has a radius of 1. And what we found is that this point x comma y on the unit circle, where the height of the triangle is y and the adjacent side is x, that these x and y coordinates are simply the cosine of that angle theta and the sine of that angle theta. And in this video, what I want to do is talk about essentially how to convert the different measures of degrees on this circle to radians. And recall that 2 pi radians is equal to 360 degrees. So if you go all the way around in a circle, that's either 2 pi radians or 360 degrees. And what we want to do is consider different key values of these radians and see what they are in degrees. So for instance, what we can start with is, let's say, this angle here of 90 degrees. So we have a right angle, and 90 degrees, to convert between radians and degrees, notice on the right-hand side of this pink equation that if we divide each side by 4, then this side with degrees will simplify to 90 degrees. And 2 pi divided by 4 we can simplify to pi over 2. So 90 degrees is equal to pi over 2. If we double everything, then 180 degrees, so that's essentially the angle halfway around. This would be 2 pi over 2, or just pi. And if we go 270 degrees, we're essentially just adding another pi over 2 to this, so that would make it 3 pi over 2. So these values here, these key values, these are always helpful to know so that you can quickly relate between degrees and radians. But what we're going to do is take a closer look at some special angles, namely 30 degrees, also the angle of 45 degrees, and the angle of 60 degrees. And essentially we want to figure out what the cosine and sine are for each of these angles. So let me make some more room so that we can talk about that. So as you can see, I've redrawn the unit circle, but we're specifically looking at an angle of 30 degrees. So theta is 30 degrees, and if we want to convert this between radians and degrees, we just have to use the relationship that 2 pi radians is 360 degrees. And it looks like if I divide this by 12, that I would get 30 degrees. So 2 pi over 12 would simplify to pi over 6. So 30 degrees and pi over 6 are equivalent. But this triangle here, we're essentially trying to figure out these x and y values, or namely the cosine of the angle and the sine of the angle, since that would be the x and the y values respectively. But what you can notice is that we have this special triangle here. Since this is a 30, 60, 90 triangle, we can essentially examine that off to the side here. So let me redraw that. And what's unique about this 30, 60, 90 triangle is that it's essentially half of an equilateral triangle. So if I were to extend this and essentially draw the other half of this triangle, you can see that it's equilateral, where this top side, this top angle here, right here, this would be 60 degrees, or essentially 30 and 30 when you split it. So in an equilateral triangle, all of these side lengths are 1, so this total side length here is 1, which makes our side length, the one we're concerned about, equal to 1/2. So we're able to find this y value. This is just 1/2 due to the properties of this special triangle. And we can use the Pythagorean theorem to find this length. So we have that 1 squared is equal to 1/2 squared plus, we'll call this x since we don't know what it is, so plus x squared. Remember, the Pythagorean theorem is just you add the two side lengths squared and set them equal to the hypotenuse squared. So simplifying this, 1 squared is 1, 1/2 squared would be 1/4, since that's just 1/2 times 1/2, and plus x squared. We subtract 1/4 from each side, so we get 3/4 is equal to x squared. And taking a square root of everything, we find that x is equal to root 3 over 2. So essentially the y value here would be 1/2, and the x value would be root 3 over 2. So let me just fill this in. The x value is root 3 over 2, and the y value is 1/2. Now, something to consider is that if we drew a triangle here with, instead of a 30-degree angle, we now have a 60-degree angle, then we're essentially going to end up with the exact same triangle. The only difference is that our x and y values are effectively switched now, since the 30-degree angle is now at the top. So essentially what you can find is that the x value, this horizontal length, would be 1/2, and the y value would be root 3 over 2. So essentially we've looked at an angle of 30 degrees and we've looked at an angle of 60 degrees, which if we want that in radians would just be double this, so it would be 2 pi over 6 or pi over 3. And I said we also want to look at when theta is 45 degrees. So that's essentially right between these. We want to look at this triangle here and figure out what its x and y values are, where this angle is 45 degrees. And I know this is getting cluttered, so let me redraw it down below. And we again have this triangle where on the unit circle, this angle is 45 degrees. And we essentially want to figure out what its x and y values are, since this is what we would consider a special angle in the unit circle. So we're setting theta equal to 45 degrees, but we want to convert first between radians and degrees. So it looks like if we divide this by 8, then we will get 45 degrees. So when we divide the radian side of it by 8, we would end up with pi over 4. So 45 degrees is pi over 4 radians, which should make sense because we found earlier that 90 degrees was pi over 2, and this is half of that. Now, this triangle here is another special triangle. Let me just redraw it really quickly, but essentially what we have is a 45, 45, 90 triangle. So we have this right angle, but each of these angles is 45 degrees. And these triangles have special properties. Namely, it's an isosceles triangle, so each of these opposite side lengths, opposite these equal angles, these are each equal to each other. And we know the hypotenuse is 1, so we can just solve for x using the Pythagorean theorem. So we have that x squared plus x squared is 1 squared. Or we have two of these, so 2x squared is 1. And dividing by 2, we find that x squared is 1/2. And from here, we just have to take a square root of everything. So we get x is the square root of 1/2, which you can take a square root of the top and the bottom, so you get 1 over the square root of 2. But we want to rationalize that so we can get rid of the square root in the denominator. So we're going to multiply the top and the bottom by root 2 over root 2, since we're just really multiplying by 1. And then the numerator, we get root 2, but in the denominator, we get root 2 times root 2, and that essentially just cancels out the square root, so we just end up with 2. Since root 2 squared, the square and the square root cancel each other, and we just get what's left on the inside. So essentially what we found is that the x and the y coordinate are both this root 2 over 2. So we can say that this is root 2 over 2 and root 2 over 2 for both x and y.